Hi everyone. Let's learn how to use a graph of a derivative to learn information about the original function. First, 3 facts. If you would like to try to complete the blanks yourself, stop the video now. You can download these notes using the link in the video description. We are given a function f, and we are told that the derivative is positive on an interval. Remember, a derivative of a function tells you how the original function changes. If the derivative is positive on an interval, then the function is increasing on that interval. And if the derivative is negative on an interval, then the function is decreasing on that interval. The second derivative tells you about concavity. If the second derivative is positive on an interval, then the original function is concave up on that interval. And if the second derivative is negative on an interval, then the function will be concave down on that interval. The relationship between the second derivative and the first derivative is the same as the relationship between the first derivative and the original function. The second derivative tells you how the first derivative changes. So, if the second derivative is positive, that will mean that the derivative is increasing. And if the second derivative is negative on an interval, then the first derivative will be decreasing on that interval. Now we are ready to use a graph of a derivative to determine information about the original function. In the problem below, we are given the graph of the first derivative, and we must first find the intervals where the original function, which we don't see, is increasing, and the intervals where f is decreasing. Remember, this is not the graph of f, this is the graph of f prime. Thanks to the first exercise, we know that when the derivative is positive, the original function is increasing. Let us find places where the derivative is positive then. I believe the derivative is positive whenever this graph is above the x-axis. And this graph is above the x-axis here, here, and here. Which means that the intervals where f is increasing are here, here, and here. The intervals are negative infinity to negative 6, negative 2 to 0, and 5 to infinity. Whenever the derivative is negative, the function will be decreasing. And I see that the derivative is negative here and here. The intervals are negative 6 to negative 2 and 0 to 5. The next 2 questions are asking us to find the value of x where f obtains local maxima and the values of x where f obtains local minima. Local maximum occurs in places where the function goes from increasing to decreasing. Local minima occur in places where the function goes from decreasing to increasing. Do we know places where the function goes from increasing to decreasing, the original function that we don't see? I believe we said that at first the function was increasing and then it was decreasing, which means up to here the function is increasing and after that it is decreasing. This means that negative 6 gives you a maximum. That is the place where the function goes from increasing to decreasing. What happens next? Between negative 6 and negative 2, the function is decreasing, and at negative 2, the function becomes increasing. So it goes decreasing and then increasing. We must have a local minimum at negative 2. This place must give us a local minimum. I continue. I see that the derivative is positive on this interval and it's negative on this interval. At this place, the derivative changes from positive to negative, which means the original function goes from increasing to decreasing. At 0, I get a local maximum. Finally, at 5, the derivative changes from being negative to being positive. which means the original function goes from decreasing to increasing, and I get a local min. How can we find the intervals where the original function is concave up? And how can we find the intervals where the original function is concave down? To find the intervals where the function f is concave up, I suggest we look for places where the derivative is increasing. Let me show you why. I believe the derivative is increasing, for example, here. Because the derivative is increasing there, the second derivative will be positive there. Think about it the following way. The second derivative can be thought of as slopes of tangent lines to the graph of the first derivative. And note that all of those slopes would be positive, meaning the second derivative is positive there. And because the second derivative is positive, the original function is concave up there. The second place where the derivative is increasing is here. This means that the second derivative is positive there, which means that the original function is concave up there. The two intervals where the original function is concave up are the interval from -4 to -1 and the interval from 4 to infinity. To find the intervals where the function is concave down, I will look for places where the derivative is decreasing. I believe the derivative is decreasing here, and the derivative is decreasing here. The intervals are from -infinity to -4, and from -1 to 1. Finally, we must find the values of x where the original function f has inflection points. Remember, an inflection point is a point where the original function changes from concave up to concave down or from concave down to concave up. We know that the original function f was concave down first, and then at x equal to -4, it changed to being concave up. This tells you that x equal to -4 is the x-coordinate of the first inflection point. The function is concave up between -4 and -1, and then at -1 it changes to being concave down again. This tells you that -1 is the x-coordinate of the second inflection point. The function is concave down between -1 and 1, and at 1 the function changes to being neither concave up or concave down, because on this interval the first derivative is neither increasing nor decreasing, which tells you that on this interval the second derivative is 0, which tells you that the function is not concave up and the function is not concave down there. Finally, at x equal to 4, the function changes into being concave up again. However, it does not change there from being concave up to concave down or from concave down to concave up. The same way, the function didn't change from concave up to concave down or from concave down to concave up at x equal to 1, which tells you that 1 and 4 are not x-coordinates of inflection points. The final thing I want to mention is that these values, -4 and -1, places where inflection points occur, are also places where the first derivative has their critical numbers. These are the critical numbers of the first derivative, because these are the places where the first derivative has the derivative equal to 0. The second derivative there equals 0.